This paradox strikes right at the heart of modern science. The deeper a researcher dives into a subject, the more specialized they become, and yet academic positions remain few and highly constrained. Universities often advertise openings in broad categories: physics, chemistry, material science. But committees are really looking for something narrower, like quantum condensed matter with focus on 2D materials, or energy materials for hydrogen storage. If your expertise lies in rolled-up nanomembranes, catalytic nanomotors, or quantum biology, there may never be a neat box labeled exactly for you. Isn't it strange that science, which celebrates innovation and diversity of ideas, often rewards conformity to predefined search profiles? This situation creates a kind of mismatch. On the one hand, science has exploded into thousands of specialized directions: nano-optomechanics, AI-driven drug discovery, microfluidic organ chips, quantum cryptography, and countless others. On the other hand, universities may only have one or two positions every few years in a given department, and those positions are tied to funding priorities, teaching needs, or political decisions within the faculty. It is a little like having an orchestra with thousands of unique instruments invented by curious musicians, but only hiring players for violins and flutes because those are standard. How then can the inventor of a brand new instrument ever find a place? One path many scientists take is to frame their specialization in terms of broader themes. For example, instead of presenting yourself as only a nanomotor researcher, you might describe your work as contributing to energy harvesting, catalysis, and biomedical sensing, which are key words committees recognize. But doesn't this raise another paradox? If everyone must translate their uniqueness into common language, do we risk losing the very novelty science depends on? Another less discussed fact is that universities sometimes hire based not only on research fit, but also on teaching gaps, industry partnerships, or even who can attract international students. A plasma physicist may be chosen because they can teach interactory electromagnetism, or because their lab appeals to aerospace companies. In this way, a scientist's job prospects may hinge less on their deepest specialization and more on their ability to connect that specialization to institutional priorities. Does this mean adaptability is more valuable than depth in the job market? The paradox remains unresolved. Science thrives on ever finer specialization, yet careers demand broad fit. Perhaps the answer lies in crossing boundaries. Scientists who can show committees not only what niche they occupy, but also how their niche connects to larger systems of knowledge and society. But it raises a haunting question: how many brilliant, unique paths of research are being quietly abandoned because they do not fit into the hiring boxes of today's universities? And is science as a whole poorer because of it? Science today produces thousands of specialized topics, from quantum biology to microfluidic nanorobotics. Each discovery opens a new niche, and scholars spend years mastering very narrow questions. This specialization is essential because modern problems demand deep expertise. Yet the structure of universities has not expanded at the same rate as the number of subfields. Committees still advertise broad categories like physics or chemistry rather than hyper-specific roles. This leads to a mismatch between expertise and available positions. A scientist specializing in strain-engineered nanomembranes rarely sees job ads asking for that exact expertise. It is like a library expanding to millions of books, but only having shelves labeled fiction and nonfiction. Universities hire based on teaching needs, departmental balance, and institutional strategy, not only on research specialization. This means committees seek candidates who can cover large subject areas for students. A niche expert may struggle if their skills appear too narrow for general teaching. Institutions also prefer scholars whose research aligns with funding priorities or strategic theme. Even if someone is brilliant, their fit depends on these broader goals. This makes the paradox structural rather than personal. A plasma nanotechnology researcher may be passed over for a material scientist who can teach across solid-state physics. It is like a school hiring a teacher who can cover math, science, and history instead of one who only teaches advanced geometry. Scientific fields multiply much faster than academic positions are created. Each new subdiscipline expands conferences, journals, and knowledge, but rarely creates new faculty lines. Departments cannot grow infinitely due to budgetary and space limits. As a result, countless subfields compete for the same limited categories. The imbalance creates systemic underemployment among experts. The paradox arises because science rewards specialization while academia rewards breadth. Quantum sensing is booming, yet most job postings still just say experimental physics. It is like inventing dozens of new sports, but only having Olympic medals for running and swimming. Hiring is said to be merit-based, but fit often overrides excellence. Committees evaluate whether an applicant can meet teaching, research, and funding expectations within the department's scope. A hyper-specialized scientist may not be rejected because they lack quality, but because they do not fit the profile. Thus, outstanding scholarship can be invisible when it falls outside defined needs. Meritocracy is filtered through institutional convenience. This reinforces the paradox for specialized scholars. A pioneer in liquid crystal nanomaterials may not fit a call for energy storage materials. It is like having a Michelin star sushi chef applied to a restaurant looking for an all-purpose cook. Because of the hiring paradox, many scientists reframe their expertise in broader terms. They present themselves as contributors to hot fields like AI, sustainability, or biomedicine. This marketing helps them survive in competitive searches. However, it risks diluting the originality of their real specialization. Over time, scientific identity becomes shaped by career pressure more than curiosity. This leads to a tension between authenticity and employability. A photonics researcher might market themselves as a renewable energy scientist to improve job prospects. It is like an artist painting generic landscapes instead of their unique, surreal visions to sell more canvases. One way to resolve the paradox is by framing specialization as interdisciplinary. A researcher can present their niche as a bridge across broader domains. This makes them attractive for departments seeking to expand into emerging areas. However, true interdisciplinarity requires fluency across multiple languages of science, which is rare. Committees also sometimes undervalue hybrids because they don't fit traditional categories. This creates both opportunity and ambiguity for applicants. A nanotechnologist combining microfluidics and quantum optics could apply to physics, engineering, or biomedical searches. It is like speaking several languages, but not being recognized as a native speaker by any country. Because jobs are limited, many scientists transition into industry, startups, policy, or entrepreneurship. These sectors often value highly specialized expertise more directly. Yet cultural bias in academia portrays these moves as second choices. The paradox is that niche expertise may be more useful outside universities, but scholars are conditioned to see academia as the primary path. This tension leads to frustration and wasted potential. Rethinking career value is part of solving the paradox. A synthetic biologist might find more opportunities in biotech startups than in university hiring pools. It is like a master baker refusing to open a bakery because they only want to work in a Michelin star kitchen. Research funding priorities differ across countries, creating mismatches between where topics thrive and where jobs exist. A subfield may be heavily supported in one nation but ignored in another. Scientists must often relocate to find alignment, but mobility is restricted by visas, family, and language. This means that some experts remain unemployed despite global demand. The paradox becomes geographic as well as institutional. Knowledge is global, but hiring remains local. A marine robotics expert may find strong demand in Norway, but no matching positions in Australia. It is like growing a crop that thrives in one climate, but trying to sell it in another where it will not grow. Ultimately, this paradox challenges the very model of academic employment. Universities may need to rethink rigid departments and create more flexible research hubs. Positions could be designed around problems, not just disciplines, to absorb niche expertise. Funding agencies could also recognize new subfields more quickly in job creation. Without such reforms, specialization will keep outrunning institutional categories. The future of science may depend on reimagining the academic job system itself. Innovation hubs like the Wyss Institute at Harvard were created precisely to bypass narrow departmental hiring. It is like remodeling a house's foundation instead of forcing new rooms into old walls.